Thanks to one of you, I can increase the speed. And actually, thanks to all of you for your patience. And some of you have actually been very helpful in making suggestions or offering to make suggestions. So let's make sure that the pen is working. Okay. Okay, so let's just start out with a little definition. What a mess. You know, I saw or heard an ad for a tablet that, I don't know how it works. I guess the top must be some sort of glass, but they say it feels like writing with a pen or pencil on paper, which would be very helpful. But okay, so this is definition. Two non-zero integers a and b are relatively prime or coprime or prime to each other if the greatest common divisor is 1. And remember the notation for greatest common divisor? Well, I'll write it both ways. So for instance, let's say 8 and 9 are relatively prime because the greatest common divisor between 8 and 9 is 1, even though, notice, neither 8 nor 9 is itself a prime. So, all right, so there's a difference between two numbers being relatively prime and an individual number just being prime. Okay, so let's just recall we showed that if A and B are two non-zero numbers those words are too close. And as usual, numbers means integers. Then the smallest positive number, integer, the smallest positive number expressible as a linear combination of A and B. So that's AX plus BY. It's a linear combination of A and B, is the greatest common divisor. Of A and B. So this does two things for us. So this says if D is the greatest common divisor of A and B, there exist integers x sub 0 and y sub 0 such that ax sub 0 plus by sub 0 equals D. Or, of course, the other way around, by the symmetric property, you could write D equals ax sub 0 plus by sub 0. So this does two things. It shows us that the greatest common divisor of two non-zero integers A and B always exists. And it tells us the form. It tells us what it looks like. It tells us how it can be written. So we showed that last Thursday. Then on the basis of that theorem last week, we showed that if a prime number P divides a product of two non-zero integers, I mean, every number divides 0, so that wouldn't be saying anything, but two non-zero integers, and it meaning P, and P is prime to one of the factors in the product. It divides the other factor. So So up here, prime to each other or relatively prime. Sometimes you say co-prime, usually relatively prime, often prime to each other, sometimes co-prime. They all mean the same thing. Don't sit down and memorize them. Know what one of them means. What's that?
Dr. Friedland, what do we exactly mean by relatively prime? What is the emphasis on that relatively, specifically that word? Why can't we just say prime, P-N-A-R prime? I know there's a significance.
I want to be fancy and use the color. So relatively prime means the greatest common divisor is 1. And so A and B are relatively prime if their greatest common divisor, written as just the ordered pair of integers A comma B, is 1. So over here in this example, 8 and 9 are relatively prime because the greatest common divisor is 1. 1 divides all numbers, but no bigger number divides both 8 and 9, even though neither 8 nor 9 is itself a prime. So let me go back to black color. So yeah, that's the difference. A number itself is prime if its only positive divisors are 1 and itself, such as 11 is divisible by just 1 and 11 and nothing else, versus say 10, which is divisible by 2 and 5, as well as 1 and 10. When you talk about relatively prime over here, relatively prime at the top, we are talking about 2 or more numbers. We'll be dealing with 2 numbers whose greatest common factor is 1. Sometimes you deal with whole sets of numbers, and you might speak of them as being relatively prime in pairs, meaning any pair of them is relatively prime. We'll be really dealing with just 2 numbers. So up here where it says definition, 2 non-zero integers are relatively prime if the greatest common divisor is 1. And observe that in that case, from this theorem, we showed that if A and B are non-zero numbers, integers, then the smallest positive number expressible as a linear combination of A and B is the greatest common divisor of A and B. So if A and B are relatively prime, that means their greatest, up here, relatively prime, their greatest common divisor is 1, over here, greatest common divisor is 1. And that means the greatest common divisor of relatively prime numbers, namely 1, is the least positive number expressible as a linear combination of A and B. And since 1 is the least possible positive integer, 1 can be expressed as a linear combination of A and B. And so on the basis of that, we showed that if prime divides a product, if it's prime to one of the factors, it divides the other factor. So if, in this last line here, if the greatest common divisor of P and A is 1, close parentheses there, and P divides AB, then what? If P is prime to A. P and A are relatively prime. And here's P dividing a product. And what the theorem, the last theorem we had Thursday, and we're going to prove another theorem momentarily, which uses the same kind of tactic. We proved, and it's not a difficult proof, you should be able to prove that, if the greatest common divisor is 1, then from this preceding theorem, 1 can be, as I was just saying, and as the theorem says, 1 is expressible as a linear combination of A and P. So that means there's an X and Y such that a linear combination of A and P, AX plus PY equals 1. And remember what we did then? We wanted to get B involved, so we multiplied through by B. And we saw that on the left-hand side of that equation, each term had a factor of B. So you could pull it out and show that P divides what you get as B on the right. That is, if you take the linear combinations, it's equal to 1. Here it is, linear combination, AX plus PY equals 1. Well, I just said it, and we did it on Thursday. Multiply through by B, so now you have B on the right instead of 1, and that would show, if you look at the left side, that P divides B. So the conclusion of this is if P divides AB and A and P are relatively prime, that means their greatest common divisor is 1, then P must divide B. So that's what we proved on Thursday. Let's prove a similar theorem. By the way, notice as we do all this, as always happens in mathematics, it's set up so that one thing leads to another. So we had the division algorithm. We used the division algorithm to prove the theorem last Thursday that said that the greatest common divisor of non-zero integers A and B is the least positive integer expressible as a linear combination of A and B. Then we used that to prove the theorem I just reminded you of, namely that if P divides a product, prime P divides a product, it's prime to one of the factors, it divides the other. Now let's prove a similar theorem that says if a number, say C, divides a product, say AB, and C is prime to one of the factors, it divides the other. And again, prime to one of the factors up here, relatively prime to each other. So that means suppose C, which divides AB, is prime to one of the factors, and we sometimes say without loss of generality, suppose it's prime to A, it doesn't matter. If it's prime to B, you can switch, it doesn't matter which it's prime to, as long as it's prime to one of them. Suppose C is prime, for instance, just to be specific, to A. So we have C divides, let me write this separately, then I'll write equals. C divides AB, that is, there exists some number, I don't know, D, such that, so what does it mean to say C divides AB? It means AB equals C times something, say D. And we also have that the greatest common divisor, C is prime to A. That means by definition, prime to each other means the greatest common divisor is 1. So from the theorem, that we did Thursday that I just mentioned several times about the greatest common divisor and linear combinations, we have that the greatest common divisor of C and A is 1. And so 1 is expressible as a linear combination the greatest common divisor 1 of C and A is a linear combination of A and C. So AX plus CY equals 1. Or the other way around, you can put the C first. It doesn't matter what you put first by the commutative property of addition. Okay, so we're going to do exactly what we did on Thursday. So we want to get a B in there. So we get A, B, X. I'm multiplying B into each term on the left side and the right side, plus B, C, Y equals B. And we want to show that C divides B. But somewhere we have that C divides AB, and therefore, where is that? I'll write it. Okay, so C divides AB implies, did I write that? Okay, implies AB equals, oh yeah, okay, here it is. Okay, so I'll rewrite it. AB equals CD. So this linear combination so instead of AB, we'll write CDX plus BCY equals B. Or if we factor the left side, we have a C there and a C there. We have C times dx plus dy equals B. And that's the definition of C dividing B. And you make some concluding comment. Okay, so this is really easy. I've, as usual, done an excess of writing to make every tiny detail clear, but it's really the same kind of thing that we did on Thursday with the prime. So just to summarize this, what do we have? If C is prime to A, and C divides AB, then AB is C times something, so over here, which I rewrote over here. And since the greatest common divisor of C and A is 1, from that important theorem we had on Thursday, C1 can be written as a linear combination of C and A. So A times something over here plus C times something equals 1, the greatest common divisor. And then what we do is multiply through by B, and that basically puts a B here and a B here. And then we have clearly C divides this term, and since we're given that C divides AB, C divides the left side. You can pull it out and show it separately if you like over here. Or you can just say, since C divides the left side, C divides the right side, so C divides B. So we have that. Okay. Now let's start. Let's call this beginning. We're not up to Diaphantine equations yet. We have a few preliminaries, but beginning of topic on Diaphantine equations. So this is named after Diaphantus of Alexandria. Circa means around 3rd century of the Common Era. So, you know, in those days, people didn't have last names. So, well, even now, some last names are indicative of places people have come from. So, Diaphantus of Alexandria, nothing really. He was a prolific author. He wrote on geometry and on algebra, and especially on number theory. And he considered only equations or solutions to equations with integral values. So you know, basically nothing is really known about him personally, not even his nationality. Alexandria had a major university and library that was Greek, but it was also in Egypt and Africa. And it's almost certain that while many of the people who were associated with the university in Alexandria were Greek, it's almost certain that many of them were also Egyptians or other Africans. So, as I say, not too much is known even about his actual nationality. But some of his works are extant, 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 it means they still exist. Many of them are just, lost to the dimness of time, a couple of thousand years. So a Diaphantine equation is an equation whose coefficients and the constant term and the solutions must all be integers. So, for instance, the problem of deciding in how many ways, say $25 can be paid in $2 and $5 bills gives rise to a Diaphantine equation, namely, for instance, suppose X is the number of $2 bills and Y is the number of $5 bills. So mathematically, okay, so a certain number of $2 bills, say X $2 bills, so there are X of these twos of his times, so that will give us X bills at $2 each is 2X dollars plus, and then Y $5 bills, Y of them is 5, each one is $5 times the number of $5, the number of $5 is, I guess, is 25. And of course, it's probably illegal to deface money, so you're not going to tear up a $2 bill or a $5 bill and have a fraction of a bill. No, X and Y have to be whole numbers, right? A whole number of $2 bills and a whole number of $5 bills. So that leads to a Diaphantine equation. So let's take a look at the theorem that says the Diaphantine equation, say ax plus by equals n, has a solution if and only if the greatest common divisor of the left side of A and B let's just take a look here. If one of that, well, if A and B are both 0, you don't have an equation. Well, you have an equation, but the equation becomes just 0 equals 0. Okay. If one of them is 0, say suppose B was 0, but then you just have AX equals N, so you know what B is. So y can be anything, and then you just have, it's trivial, then you just have AX equals N. So what we're saying here is the Diaphantine equation AX plus BY equals N has a solution if and only if if and only if the greatest common divisor of A and B is a divisor of N. So for instance, say 6x minus 14y equals 45 has no solution. Well, because the greatest, according to this theorem, the greatest common divisor of 6 and 14, which is 2, doesn't divide 45. But we can also just look at it and say, right, the left side is an even number. It has a common factor of 2, semicolon. The right side is odd. And of course, an even number doesn't equal an odd number. So just by looking at it, even without any kind of theorem, you know that can't have a solution. Let's prove this because it's an important step towards the general procedure for solving a Diaphantine equation like that. So suppose D is the greatest common divisor of A and B. So that, remember what that means. D divides A, or A equals D times some number, and D divides B, and that means B equals D times something, say B sub 0. So then this Diaphantine equation over here becomes, using what A is and what B is, so it becomes A equals D A sub 0 X. There it is, that's what A is. D A sub 0 then times X plus. Now we have B, but B over here is D B sub 0, and then we have a Y over here. And we can see that this is D times A sub 0 X plus, taking out the D, D sub 0 Y equals N. And that's a statement that D times something equals N. That's a definition of D dividing N. So if and only if, it has to go both ways. So we have to look at the converse. So far we showed that in order for this Diaphantine equation to have a solution, the greatest common divisor of D of A and B has to divide N. And now suppose that so remember about how to read that. It's not suppose D equals the greatest common divisor of A and B. It's suppose D which equals the greatest common divisor of A and B divides N. So we are supposing here we'll have a whence. Whence means from which. Try that again. So that there's some number, say n sub 0, such that n equals d n sub 0. But we have that D is a linear combination of A and B. So since So we have that D equals A times some X sub 0 plus B times some Y sub 0. And if we multiply through by N sub 0, we get D N sub 0 equals A, multiplying through everything there by N, A by N sub 0, A N sub 0 X sub 0 plus B, and again, I'm multiplying through by N sub 0, so it's going to put a factor of N sub 0 there, Y sub 0, but since this D N sub 0 is N, we have since N equals D N sub 0, we get N equals A N sub 0 X sub 0 plus B N sub 0 Y sub 0, or again, it doesn't matter which way you read the equal sign. So since I have the N here on the right side, I'll put the N on the right side. And let's write this on the left side as A parenthesis over here, A parentheses N sub 0 X sub 0 plus over here B, and by the associative law, just put in N sub 0 Y sub 0, and that equals N and so look at this now. This shows that X equals N sub 0 X sub 0, and that's a value of X, and this is a value of Y. So this shows that X equals N sub 0 X sub 0, and again, it's messed up. And Y over here equals N sub 0 Y sub 0 satisfies, that means makes true, the Diaphantine equation AX plus BY equals N. So that shows that first, if D is the greatest common divisor of A and B, then D divides N. And conversely, suppose, so now you start with the conclusion over here. Suppose you say D divides N, then we just showed using the theorem on linear combinations and greatest common divisors that, in fact, you do get a solution to the Diaphantine equation. So let's show that if the coefficients are relatively prime in the Diaphantine equation, ax plus by equals, say, n, or whatever it equals, and x equals, again, when I put a subscript on a letter, it means a particular value, so it's not a variable anymore. So if x has the value x sub 0, y has the value y sub 0, is, and notice singular is, this is one solution. It has two parts. I mean, just like when you solve n equations and n unknowns, if they're consistent and you get a solution, well, you have a value for each of the unknowns, say x sub 1, x sub 2, through x sub n, but that's just one solution. So is one solution. Then all solutions let's call them x prime and y prime, are of the form, right? So we were talking about forms of integers. We still haven't gone over all of that. I would like to do so. They're of the form so they start with the particular any solution x prime, y prime starts with the particular solution that you have. You know, we have to talk about how you get that particular solution, but if you do have it, x is of the form a particular value of x plus k times b, and y prime, I'll move it over, y prime equals a particular value of y minus k times a for any, right, upside down capital A, for any k and z. And remember, for any means for every. So let's see. You know, yeah, go ahead.
We wrote y prime is equal to y naught minus k times a, correct?
Yeah.
For every k an integer?
Yeah.
Thank you.
And so notice, yes, thank you for bringing that up. Notice that, any solution is of the form a particular solution plus any k in the integers, and there's an infinite number of them, times b, whereas the y value that satisfies it is of the form a particular value y minus k times, it's not the greatest day, I guess. Minus that same k times a, but that's true for any, so we had to show this, but that's true for any integer k. So that indicates that again, if one of them say b is 0, then this Diaphantine equation ax plus by equals n, where if it has a solution, the greatest, if b is 0, that's out, so you just have ax equals n, and the greatest common divisor of a and b, well, any number divides b, so the greatest common divisor of a and 0 would be a itself, so a divides n, and you get a solution. So yeah, it's trivial, as I said before, if b equals 0. So suppose a and b are not equal to 0, the equation the Diaphantine equation ax plus by equals n has n okay, this says the Apple Pencil battery is low, 5% battery remaining. So I suppose I should reinsert the.
Well, it'll be enough to end the class. I mean, usually the pencil goes on like 24 hours, so 5% of 24 hours. I think that's enough time.
Oh, okay. Because I had charged it a lot before, but okay, fine. Yeah, it's like 5 to 7 already anyway. The equation, yeah, has an infinite number of integral, and again, as I've used that as an adjective before for integer. Solution. So I point out that this may be new to you, and presumably it is, but it's not mathematically difficult. In no case in all these proofs, including this one and the others, are we transcending a first year of elementary algebra. So since x prime, y prime is a solution, that means when you put x prime, y prime of the equation, x prime, y prime into the equation, it satisfies the equation. So we can write over here this ax plus by equals n, as since x prime, y prime is a solution, ax prime plus by prime equals n. So we have that. And since x sub 0, y sub 0 is also a solution, we can write ax sub 0 plus by sub 0 equals n. And if we subtract the left sides and subtract the right sides, look at what we get. We get, I can think I can do sort of like 2 steps in one. So I lined it up so we have similar coefficients under and above each other. So this is ax prime minus ax sub 0. So let's just take out the a and write a times x prime minus x sub 0 plus, again, I'm subtracting the left sides and the right sides of the second equation from the first equation. So that'll give us by prime minus by sub 0, take out the b, and we're left with y prime minus y sub 0 equals 0, because we have n on both sides. And we can, let's write that as a times x prime minus x sub 0 equals negative b. Put the second term there on the right side. And the right side so far is 0, so it'll be negative b times y minus y sub 0. And that shows by definition of divisibility, so all these things that we built up to, showing that b divides a times x prime minus x sub 0. So we have, let's say in words what this is. B is dividing the product a times x prime minus x sub 0, but we started with, over here, look where it says theorem, a comma b is 1. B is prime to a. That is the greatest common divisor is, it says it right here in the hypothesis, the greatest common divisor is 1. B is prime to a. And so the first theorem we started out with today says that if a number divides a product and it's prime to one of the factors, it divides the other. So
Dr. Freeland, when you have a chance, I have a question.
yep.
So it doesn't matter that we're saying that B divide positive A open parentheses X prime minus X naught parentheses close. Shouldn't after the divisible bar, it should be negative A as a coefficient, or
No, over here, over here, a times x parentheses x prime minus x sub 0 is b times something. It's b times negative y prime minus y sub 0, but I don't care. I have a factor of b there. So that says b divides a times x prime minus x sub 0, right? A time over here, a times x prime minus x sub 0 is b times something. Times something, meaning some integer. So B divides this. So B divides the product, but we started with the fact that B is prime to A. From the first theorem today, B must divide the other factor, which is x prime minus x sub 0. So what does that say? It says B divides x prime minus x sub 0. Or again, what does it mean to say that B divides x prime minus x sub 0? It means x prime. Well, let me just actually remind you. Going back to the definition of divisibility, that's correct. X prime minus x sub 0 equals some multiple of b. And so x prime equals x sub 0 plus kb. So we have that, and we'll conclude this by observing that so if we put kb in for x prime minus x sub 0 in a times x prime minus x sub 0 equals negative b times y prime minus y sub 0. And so we have that over here. And so it becomes a, and then this x prime minus x sub 0 is kb. So it's a times kb equals negative b times y prime minus y sub 0. And now AKB. This KB is x prime minus, let me rewrite that. Okay, so this up here becomes A, and then x prime minus x sub 0 is KB, and that equals negative B times y prime minus y sub 0. And now going back to the cancellation law in an integral domain.
How am I going to watch? Now I'm hot. Now I'm cold.
And so here we have.
Can you move your leg forward? Because I can't move.
So here we have in this last equation, we have b on both sides, and in an integral domain, we can cancel non-zero factors and get.
Okay, fine, I'll leave you alone. No, not leave. Stop
I
talking
think
to
someone's
me.
unmuted.
Okay, thank you. All right, so we can't see the b here and the b here in an integral domain. We can cancel non-zero factors, and we get ak equals negative y prime minus y0, or ak equals negative y prime plus y sub 0, or let's put that over there, put the ak on the other side, y prime equals y sub 0 minus a times k. So so we have, let's just summarize this. What we've shown is if x sub 0, y sub 0 is one solution to ax plus by equals n, all solutions are of the form x prime equals x sub 0 plus kb, and y prime equals y sub 0, a particular value of y minus a k, where k is an integer. Okay, so we'll leave it at that for today. On Thursday, let me have you do this. This all started by assuming that there is over here, all solutions x prime, y prime are of this form, but I'm assuming that there are other solutions. Maybe there aren't any other solutions. So you have to prove that this x prime, y prime actually is a solution of ax plus by equals n. Let me conclude by just coming back, and this is a slightly subtle point. What we've done so far is we have, on the basis of the assumption that there's another solution, if there's another solution, the solution is of this form, that. If there's a solution, it has to be of this form, but we assume that there is another solution. Again, if there's another solution, it has to be of this form. Now you have to go back and prove that it is an actual solution. How do you do that? In the usual way of checking an equation, you do it by substitution. So that's pretty trivial. So do that, and on Thursday we'll actually see how we can use what we've developed today to actually solve real Diaphantine equations, including, say breaking $25 into $2 bills and $5 bills. So let me come back to you and conclude the recording and see if anyone.
Dr. Friedland, I have a question on the notes. I have a question on if we may scroll up a little bit, please. I just want to, maybe the way it's written, I'm not sure if it's a subtraction or not.
You mean over here where it says subtract?
Over there, but we started with the order pair A, B is equal to 1. Is that 1 minus B is a prime to A, or are we saying that as the hyphen, B is a prime to A?
Yeah, I guess that's bad. Yeah, it's a hyphen, or it's actually a dash.
A dash.
Yeah. Yeah, you hyphenate a word, but when you're separating words, you use a longer line called a dash. Okay, so I will get back into Zoom and stop broadcast and press that and press more and do that.
The recording has stopped.
And okay, so put myself back there. Okay, that's it. Again, what we've done is not profoundly difficult. It's not subtle, but it's not automatic either. So, go over it and, make sure you understand the follow through because as always happens in mathematics, we're building on what we've already had. We've already done it today. We'll continue on Thursday. So that will complete the formal class for today. Anyone wants to stick around and ask any questions, you can. If not, I'll see you on Thursday. And tomorrow is Monday.
Thank you, Professor.
Thank you, Dr. Friedland.
Okay.
Thank you.
Okay, then. We'll get together again Thursday. See you then. I'm going to end it.